So what we have with horizontal and oblique asymptotes is that there's three possibilities. Okay, the first one is what we saw when we did 1 over x, and that's going to be the x-axis, or when y is equal to 0. And this is any time that the numerator degree is less than the denominator degree. So it could be x plus 2 for our numerator, x squared minus 9 for our denominator. These values that we're adding and subtracting, they don't really matter for our horizontal asymptote because that ratio will be affected very little by those as x grows very large. Okay? So at the beginning, when x is 0, right, those make a big difference because you have 2 over 9. But if I go to some very large value, like 1 million, right, 1,000,002 divided by, then I take 1 million squared, right, so very big. Am I subtracting them? So that'd be like 12 zeros, I think. So then that'd be 9, 9, 9, 9, 9, 9, 9, 1, right? So that plus 2 and that minus 9 will make a very small difference in terms of it's almost a million over a million squared. And what you'll see is that the bottom, because it's a higher degree, is going to outgrow the top. So as we get closer and closer, that's part of our definition. As x gets closer and closer to infinity, bigger and bigger, this ratio, even though I have a million on top, I've got 999 billion on bottom. F of x is going to approach 0. And that's, the degree can be greater by 1 or 2 or 3. If the bottom is a higher degree, overall it's going to get closer to 0. And so this is a tiny bit like in, I don't know, do you do, I think calc's only where you do limits, but trig, I don't know if you do, where you're looking at what happens as x is just getting bigger and bigger. So again, what am I looking at in the function to decide? You're looking at the degree. Do these numbers matter? They don't. So degree is what you need to pay attention to. Yeah. All right, so the second one is, what if they have the same degree and they grow at the exact same speed? Right? As x is to the first, the bottom has x to the first. Or x to the second over x to the second. So an example for that might be f of x equals 3x squared plus 2 over x squared minus 4. So there again, what numbers don't matter? Yeah, the plus 2 and the minus 4 are incidental here. They matter a lot at the center of the graph, right, where the asymptotes are, stuff like that. But on the extreme values, we're ignoring those. And we're looking at, hey, I've got x squared on top, x squared on bottom. So whatever number I put in, I'm going to get x squared divided by x squared is just 1. But the top is how many times bigger? It's 3 times bigger. And so in this case, when they're growing at the same rate, right, what you want to say is that you need to compare how many of the top you have compared to the bottom. So for every x squared on top, I have 3 compared to 1 on the bottom. So here, it's going to approach to the value of 3 over 1, which is 3. So you can imagine, if you put a billion in there, square that, and think of the name for that. For billion, it's like 18 zeros, right? You have 3 times that on the top, and 1 times that on the bottom, and then tiny, tiny difference. It's going to be very, very, very close to 3. It's going to be a little bit more than, they got plus on the bottom and minus, plus on the top, minus on the bottom. So it might be 3.0000000 something. It's approaching that value.